Hey, what's up everybody? Hope you're all doing really well. Welcome to 2018. I hope you spent some good time with your friends and family, brought in the New Year's. For this video, I want to talk about a couple current events. If you haven't heard, there's a couple crazy security vulnerabilities going around in the news called Meltdown and Spectre. These are really badass names and pretty crazy problems. A lot of the technical details are going to be way over my head. But the whole point of this video is that we're going to talk at a pretty high level, and that by the end of this video, everyone's going to have a basic intuition of what Meltdown and Spectre are. So let's do it. So the first thing that we have to cover is different levels of optimizations that happen on a computer system. So to be very general, I broke this down into three broad categories of optimization. The first level is where we all operate at as software developers, and the highest level of optimization just happens at the software development level. And this is how we write our code. So unless you purposefully do something really bad, you can't really mess up at this level. So this is like saving computations, caching things in memory, basic software development stuff to speed up your program. So at the highest level, we have optimizations with software. All right, so we just talked about the highest level of optimizations, which happen at the software level, at the programmer level, and now we're gonna go one step below that and talk about machine level optimizations. So at this level, we already can't really control the optimizations too much. We can't really control what the compiler is doing besides a couple tweaks in the parameters. We can't really control what the crazy runtimes are doing to optimize all the dynamic things that are happening. But this level is already beyond us, and this is also the reason nobody really writes assembly code, right? Because nobody writes assembly code because you're not going to do it better than the compiler does it. So this is the second level of optimizations. Compilers and runtime are going to kind of generate the best possible machine instructions that they can, so to feed it into the CPU. Because remember, the CPU's job is just to execute instruction after instruction after instruction, and it's being told what instructions to execute. So we gotta feed it the best possible instructions, and that's the job of the compilers, and that's already beyond us. Now finally, we're gonna talk about the third and lowest level of optimizations, and this is going to happen at the hardware level. At this level, we have hardware designers, hardware architects. Those are the type of people thinking about CPU level optimizations, and this level is extra crazy because in an ideal world, we're going to feed the CPU perfect instructions that are compiled from the best software, right? But in reality, even if you give a CPU good software or you give it crappy instructions, good instructions, the hardware itself is going to do its own level of optimizations irrespective of the instructions you give it. So a lot of the different hardware techniques that a CPU uses are going to be beyond the scope of this video and my personal expertise, but a couple examples of CPU level optimizations are sometimes the CPU can look a little bit ahead in memory because remember, you have a huge stream of instructions. You're doing it one at a time. Sometimes the CPU just looks a little bit in the future to see what's going to happen. That's one technique. Another technique could be, it could add multiple sets of numbers that don't depend on each other. So it could do 4 plus 4 here and 8 plus 8 here at the same time because it knows those two numbers don't depend on each other. And it does a lot of crazy smart things. It's beyond the scope of this video, but remember, at the hardware level, crazy things are happening. Okay, hopefully you're still with me, but we really needed to do this kind of background talk before we talk about Meltdown and Spectre. So to recap, the three levels of optimization, highest level, software level is what we do as programmers, remember. Second level is compiler, runtime, and machine level optimizations, wizard stuff. And finally, the lowest level of optimizations happen at the hardware level, and unfortunately, that's the level where Meltdown and Spectre happen. The first thing we have to talk about at the lowest level of hardware optimizations is a really common technique known as branch prediction. Branching is a pretty easy thing to understand for anybody that doesn't write code. It's just different flows of logic that your program can potentially take. So if this is true, do that. Else, do this. It's just basic logical flows, and that results in this thing called branching. So just like real life, the CPU can detect patterns and habits of the software. Just like you and me have habits, we go to the store every Friday, we go grocery shopping every Sunday, we like to go work out every Monday. Those are different flows in our life logic, and they all have patterns, right? But similarly, in software more or less executes roughly the same thing over and over and over again. Because think about what you do on your computer normally. You open up Chrome, you open up a few tabs, you type with your friends, or you send messages with your friends, you play the same games. Would you probably update your software every few weeks, maybe every month, but overall, the software that runs on a processor has a lot of patterns in it, and the CPU starts learning those patterns. So one really cool thing that modern processors all do is branch prediction. So remember branching. If this, else that. If this, else that. But one thing that they do is they can keep a history, a branch history table, but every processor keeps a history of all the different branches taking, and it slowly can develop patterns of what's taken more. So if you take a branch 80% of the time, if you go through this flow of logic 80% of the time, the CPU is logging the history of that. And since it knows it happens most cases, it's gonna predict that it's gonna happen for the next time. So this is kind of the essence of branch prediction. It just tracks the history of your logic flow so it knows what's highly likely to happen in the future. It's a crazy hardware optimization technique. Think about how technical this stuff really is, but the intuition, the essence of it is still really, really basic. This is just like every Saturday your girlfriend goes grocery shopping. Like every Saturday she goes grocery shopping, so you start expecting that every Saturday evening you have the home to yourself, right? Because that branch of logic happens so often, you just start predicting it. So let's just keep going with this analogy, okay? So let's assume my girlfriend, every Saturday she goes out grocery shopping, and I get used to it. Like 80-90% of the time, every Saturday she just goes grocery shopping. Well, sooner than later, before she even tells me she goes grocery shopping, I'm gonna actually start inviting my friends over Saturday, because probably she's gonna be out and my friends can come over, right? Worst case scenario, 10% of the times I have to tell my friends they can't come over. But usually if she goes grocery shopping, I've already invited my friends, I've already done that work, and they just come over and we have a good time on Saturday night. If we take those concepts back to processor land, so imagine you have a special piece of code that's, if some kind of conditional is true, execute this special piece of code. If the processor detects that that conditional is always met, if it detects that branch is gonna happen all the time, it's gonna actually do those instructions ahead of time. And that's actually the essence of speculative execution. That's also where Spectre comes from, but speculative execution is the processor executing instructions ahead of time based on its branch prediction. All right, so if you're still with me, at this point in the video, you should have an intuition of what speculative execution is. The processor is doing instructions ahead of time because it thinks a branch is gonna happen. So it's just doing things, it's looking ahead and doing the work up front for you. And this is analogous to, I know, or I'm expecting my girlfriend to go out on Saturday night, so I'm already calling my friends to ask them to come over. So for everyone watching, you're watching this on your smartphone, you're watching this on the computer, you're opening up Chrome or Firefox or whatever, but remember, that's just one process on your computer out of hundreds, thousands of processes that are running all concurrently on your computer right now. Chrome, you watching me on Chrome, there's just hundreds of other stuff also happening that you're not aware of. So remember that each one of those processes on your computer have to follow very, very, very strict rules. One of those rules is that your process, like the Chrome process, it can't access memory of the operating system, of the kernel. It also can't access special memory of other processes that are running. Remember, every process is supposed to execute in isolation, so you can't have one process peeking into the contents of another one. So I'm gonna put up some very pseudo code over here to try to portray what could potentially happen. So what if you purposefully want to access some of that system memory? You want to access that data that you're not supposed to access. So you purposefully put some bad reads into your code, and it's behind this branch. And for whatever reason, this branch happens pretty often. The processor detects that that branch is taken very often. So in its head, it starts detecting that it needs to speculatively execute your bad code. What some processors are actually vulnerable of is that imagine your processor is still executing that if statement, right? But it's still speculatively executing this bad code, and it starts slowly reading it into memory to get ready to use it. But at this point, and things still aren't broken yet because you haven't done the bad code per se, you've just kind of predicted you need to do the bad code. So even if your processor is still at the if statement, it's already temporarily loaded all that bad content into the processor somewhere. So technically, at this point, everything is still okay, right? Because you're still trying to evaluate the if statement. The processor is doing its own thing to read that bad malicious data into memory, but still, everything is still speculative. Everything is still okay, but it's at this very, very moment in time where an attacker can read the contents of the processor because it's loaded that bad stuff into its memory, and it still thinks everything is okay, but the attacker can kind of read into those, parts of memory it shouldn't be reading into. So that was a really high level overview of it, but that's kind of where the word meltdown comes from, because remember, every single process has very strict rules or barriers of what it can access. It can't access other processes, it can't access the kernel memory. It has very tight barriers of where it can look, but the whole word of meltdown is that the whole bug kind of melts down these walls or melts down these barriers, which enables processes to utilize speculative execution and look around in places it shouldn't be. All right, so that's my attempt at explaining a very, very technical concept. Hopefully by this point you at least have an intuition of what it means. If you want a very, very technical explanation of what Spectre and Meltdown are, there's tons of resources out there. I think the Google AlphaZero project, the team that discovered these things, they have highly, highly technical papers on it, which is way over my head. But if you're interested, go check them out. So what have people been doing to fix these problems? But a lot of companies they've just turned off the whole feature completely. So I told you, branch prediction, speculative execution, these are all features of modern processors to make them perform better. But one thing that companies have been doing is that they just turn it off. It's easy, right? If you just turn off the feature, it can't be exploited. But the side effect of that feature is that I think a lot of these processors are running 10, 20, even 30% slower than they used to be. So remember our levels or categories of optimizations. We have software at the very top, then we had machine instructions within compilers, and then we had hardware level. But the reason why Meltdown and Spectre are so serious, so pervasive, and affect everything is because they happen at the hardware level, and that's the hardest to fix. Remember, if you have a vulnerability at the software level, that's pretty easy. You just write some code, patch it up. It's software level. It's soft. You can just fix it, right? But these vulnerabilities, this exploit is baked into how the hardware itself actually works. So that's why it's so crazy. People just have to disable whole features. It's pretty crazy if you think about it, and I'm interested to see how people resolve it. But hopefully you guys got an intuition of what all these different things meant. So if you guys have any additional questions about Spectre or Meltdown, hardware vulnerabilities, whatever, leave me a comment. I'll try to answer this. Hopefully this video was helpful. Please like it, share it, and I'll see everybody next time.